In this first question, we are asked to look into the boiling point of the straight chain alkanes, which are butane, pentane and hexane. In all hydrocarbons, there's only one type of intermolecular force, and that force is known as van der Waals forces. If we look at this in a bit more detail, in this particular diagram, what you see is a small molecule such as methane, and the shaded area here and here is representing the van der Waals forces. In a small molecule such as methane, you only have a small area of surface contact, which is this over here, hence you only have relatively weak van der Waals forces. However, in a longer molecule such as pentane, you have much more van der Waals forces, and therefore the boiling point of larger molecules will increase due to higher amount of van der Waals forces. So the answer to this particular question is that the boiling point will increase with increased molecular weight or longer chain length. And the reason for that, as stated earlier, is because you have a greater number of intermolecular forces or van der Waals forces. In the next question, we are asked to look into isomers with a molecular weight of 72, and those are pentane, 2-methyl-butane and dimethyl-propane. All three of these compounds are isomers of each other. Now if we look at these particular isomers in detail, we have them listed here. So we have pentane, 2-methyl-butane and 2,2-dimethylpropane. Comparing again to the van der Waals diagram we looked at earlier, if you see a straight chain molecule, you have greater contact areas as listed here. However, in a branched molecule over here, there is much less surface area of contact, and therefore you have less van der Waals forces. So for pentane, the molecules will pack together in this format over here. 2-methylbutane has got one branch, and 2,2-dimethylpropane has got two branches. The more branching you have, the less van der Waals forces, and hence lower the boiling point is going to be. The answer the examiner is looking for is listed here, which is the boiling point increases with increased branching, or you have less surface contact and therefore the molecules cannot pack together as closely, or you have fewer van der Waals forces. In part 3 of the question, we're asked to use the table to predict the boiling point of 3-methylpentane. Now 3-methylpentane is actually an isomer of hexane and 2,3-dimethylbutane. And what we notice about these two isomers is the fact that hexane has got no branching at all, whereas 2,3-dimethylbutane has got two branches. So the boiling point of 3-methylpentane is expected to be between that of a non-branched and a dibranched molecule. So any value between 69 and 58 would be acceptable. For the explanation of why alkanes such as pentane do not react with reagents such as nucleophiles and electrophiles, what we first have to do is understand what is a nucleophile and what is an electrophile. Basically, in organic chemistry, there are three different types of chemical species which can react with any molecule. Let's look at first of all what is an electrophile. So an electrophile is a chemical species with a positive charge on it, or a delta positive, and the typical chemicals that you're going to get with such a charge are going to be, for example, something like a H plus sign, or you could talk about a Br delta positive. Now, in order for this type of species to react, you must have something that they will react with, and that would be something similar to a carbon-carbon double bond. Now, clearly in an alkane such as pentane, you do not have a carbon-carbon double bond, so therefore it will not react with this type of chemical species. So what is a nucleophile? A nucleophile is something, for example, that has a long pair, and that something could be Br minus, it could be something like OH minus, or indeed it could be something with a lone pair, such as ammonia. And in order for these type of species to attack a chemical molecule, what you need is an electron deficient center, something with a delta negative or a delta positive, and again an alkane does not have any delta positive or delta negative. And lastly, we have the free radicals, and these are chemical species with unpaired electrons in them, and these are very reactive and they can react with alkanes. However, the question is not asking about radical, it's only asking about nucleophiles and electrophiles. The answer for this particular question is first of all acknowledging that alkanes are non-polar molecules. That means they do not have any delta negatives or delta positives in them. And then what we just talked about earlier about nucleophiles and electrophiles being attracted to polar substances, or you could put down the fact that carbon-hydrogen bonds are very strong. In this essay type of question, it's very important to ensure that the three bullet-pointed items here are actually addressed individually. It's very easy for students to go off on a tangent and ignore what the original question was about. So here there are 3 bullet points, and the first one is naming and describing the mechanism for the reaction between pentane and bromine, which we'll address first. The name of the mechanism is free radical substitution, and again a reminder, alkanes will only react via free radical substitution. And then the balance equation, the question did actually ask us for the reaction between pentane and bromine, and hence we've got to make sure we've actually included here pentane and not any other alkane with bromine. The overall equation is given to us over here. Pentane plus bromine will give bromopentane plus hydrogen bromide. One of the hydrogens from here has now been extracted by a bromine atom, and this hydrogen here is now the same hydrogen over here, and one of the bromines from here has now been coupled with the hydrogen here to form hydrogen bromide. The remaining bromine over here is now the bromine which has been substituted by the hydrogen. For the mechanism, you start off by initiation, which is this over here, followed by 2 propagation steps. Now in the first propagation step, the same bromine over here is the bromine being used over here. So that will react with a molecule of pentane, forming 1 molecule of hydrogen bromide, and this is now an alkyl radical because one of the hydrogens here has been taken away from here. And then what we have next is the same molecule here reacting with another bromine molecule to produce one of the final products plus a bromine radical, which will then recycle itself back into the stage over here. And then finally, for the mechanism, any 2 radicals coming together could be a termination step, and the simplest one could actually be bromine dot plus bromine dot, giving you a bromine molecule. The type of mechanism for this reaction is homolytic fission, and homolytic fission means 1 electron goes to each atom in the molecule, as shown here and here. The last point in this question is asking us to explain why it's difficult to produce a single product in this particular answer. In pentane you have 1, 2, 3, 4, 5 carbon atoms, and any one of those 5 carbon atoms has hydrogens attached to them which could be substituted by bromine. So you could end up with a bromine over here, or alternatively you could end up with a bromine over here. And likewise you can have a bromine anywhere, for example right at the end of the chain. For the naming of compound A, we first must recognize the longest chain, and we are going to start from this end as it's closest to the functional group of bromine, and we are going to go up, and in this particular case we have 1, 2, 3 carbons in the longest chain, so therefore it's going to be a propene. We also have a substituent, which is a methyl, on position number 2. And here we have the final name, 1,1-dibromo, as we have 2 bromines on position 1. We have a methyl on position 2. Now, the mark scheme hasn't included a 2 over here. Strictly speaking, you should. However, this is completely acceptable, as the methyl can only be on position 2. And then propene for the longest chain here. For the calculation of bromine in compound A, first thing we do is work out the whole of the molecular mass of molecule A, which is equal to 213.8. We then take the molecular weight of the 2 bromines, so bromine 1, bromine 2 add up to give you 159.8, divide it by 213.8, which again is the molecular mass for this whole molecule here, times by 100 to give us a final answer of 74.7. For the structural isomers questions, there's absolutely a huge variety of answers that could be included over here. Some of the examples I will show here. Any one of these would be acceptable. I'm keen to point out there's quite a few cyclic isomers that you could have chosen from, and as a general reminder, cyclic molecules have the same general formula as alkenes. For the reaction of isomer B with bromine to prove the presence of a carbon-carbon double bond, what you must make sure of is that the reaction is actually talking about what we would see rather than what would happen. And what we would see in this reaction is the decolorization of bromine from brown to colorless. And to further emphasize this point, I'll now show a quick video of what the reaction actually shows when it happens.
The tube on the left contains the saturated hydrocarbon cyclohexane. The tube on the right contains the unsaturated hydrocarbon cyclohexene. First, brown-red bromine is added drop by drop to the left-hand tube containing saturated hydrocarbon. As the bromine is added, it dissolves in the cyclohexane. The color remains when the solution is stirred because bromine does not react with saturated hydrocarbon. Now, liquid bromine is added to the unsaturated hydrocarbon cyclohexene. The red-brown color disappears as the bromine mixes with the cyclohexene. This is because the bromine reacts with cyclohexene, adding to the double bond. This reaction is a very convenient test for the presence of a double bond in a molecule.
The type of reaction mechanism for this reaction, or for that matter any reaction with an alkene, will always be electrophilic addition. What that means is, if I have a carbon-carbon double bond and I'm adding a reagent to it, the reagent will always add across the double bond, here and here, with, of course, no more double bond. In this case, we're talking about adding bromine to each side of the original carbon-carbon double bond. In the last part of this question, we're required to find out the empirical and molecular formulae of the compound which results from the reaction of B with bromine. So if this molecule is reacting with bromine, we'll have one more bromine over here and another bromine over here. Now if we count the total number of carbon atoms, we have 1, 2, 3, 4 carbons, which are the 4 carbons here. We have 1, 2, 3, 4 bromines, which are the 4 bromines here, and we have 3 and 3, 6 hydrogens all together over here. When converting the molecular formula to empirical formulae, you cut down to the simplest whole number ratio. 4 goes down to 2, 6 is cut down to 3, and 4 is cancelled down to 2. In the reaction between isomer A and hydrogen, one hydrogen will across the double bond here, and the other hydrogen would add across the carbon here. So you end up with 2 new hydrogens, one here and one here. The conditions for the reaction are a nickel catalyst or a platinum catalyst. The reason for molecule B only having one structural isomer is because B is symmetrical, and right down the center here you have the line of symmetry. The 2 structural isomers formed when A reacts with hydrogen bromide are listed here, and if you look in detail at the 2, the first one over here can actually be formed by the hydrogen attaching here and the bromine attacking here. So that will be this hydrogen is here, this bromine is here. With the other scenario, you can actually end up with bromine here and hydrogen here, which will be this bromine and this hydrogen. The skeletal formula of 2,3-dibromobutanol is shown here. We have the longest chain in the original molecule 1, 2, 3, 4. We have the same situation here, 1, 2, 3, 4 carbons. We also have 2 bromines on position 2 and 3, and this is position 2 bromine, position 3 bromine, and finally we have the hydroxy group on position 2. The reagents for this particular conversion are steam or H2O gas. Very important you include the symbol gas here, as water alone will not actually make this reaction happen. And what you would see is the OH forming a bond with this carbon and the hydrogen forming a bond over here. The conditions for this reaction are a phosphoric acid catalyst. When drawing the repeat units of any polymer chain, it's important to recognize how many carbons are actually in the monomer. And if you look at the monomer, we have 2 carbons in the polymer backbone because you only have 2 carbons in the monomer across the double bond. We can ignore these and these for the purposes of the actual polymer backbone. And if we look at the answer, we have exactly the same situation here. We have 2 carbons across the double bond over here, and we have exactly the same situation here, 2 carbons across a double bond. We also have a methyl on a carbon and another methyl on a carbon, which is this methyl and this methyl over here. And then we have a bromine and another bromine, which is this bromine and this bromine over here. To draw the 2 repeat units, what you have drawn in 1 repeat unit, you copy exactly right next to it, ensuring that the bond here is left open, as well as the bond here is left open. Question 3a is a straightforward definition of what a nucleophile is, which is an electron pair donor, plain and simple, the easiest and the best way to answer any question regarding the definition of a nucleophile. For the reaction mechanism, you have the nucleophile in the form of the methoxide ion over here, and the lone pair of electrons from the methoxide will attack the delta positive carbon, forcing one bond to break. As you can see, carbon is already making 1, 2, 3, 4 bonds. You'll have a new bond forming by the donation of a lone pair of electrons here. And if you're making a new bond when carbon is already making 4 bonds, then clearly one bond must break, and it is this bromine here, which is ending up as a Br minus over here, because the electron pair here is now sitting as a charge over here. When comparing the rates of reaction of methoxyamides with iodobutane and then with bromobutane, the important thing to consider is the relative bond strength of the carbon halogen. Now, the right answer in this particular case will be 1 iodobutane increases the rate, and that is because the carbon bond to iodine is a lot weaker compared to the carbon bond to bromine. Let's look at this situation in a bit more detail now. Here we have the carbon bromine, and here we have the carbon iodine. As you can see, bromine is a much smaller atom compared to iodine, as iodine has one more layer of electrons or shells compared to that of bromine. If we were to draw in the relative bond lengths, carbon bromine bond length would be approximately that long, whereas carbon iodine bond length would be longer. Now, the shorter the bond, the stronger it's going to be, and the longer bond is going to be weaker. A weaker bond can more easily break compared to a relatively stronger bond. So if we're breaking this bond easier or quicker, the rate will actually increase. And here we have the official answer from the examiner, which is saying that the carbon iodine bond has a lower bond enthalpy, or the fact that they are weaker, or it's easier to break, anything along these lines. The molecule being formed in this particular reaction is butyl ethanoate, and if you look at it in a bit more detail, what we have is this CH3CO minus over here is the same CH3CO minus over here. In fact, we have a CH3CO, which is exactly what we have over here. The remaining chain over here is a part that actually came from bromobutane. And if you look at bromobutane, you have 4 carbons in the chain here. You have 1, 2, 3, 4 carbons over here. In this question, we are required to talk about the oxidation of an alcohol, and the alcohol that they have given us is propan-1-ol, which is a primary alcohol. Again, I would like to emphasize that in the question they have given us a breakdown of exactly what they require. The first indication is they want us to use different reaction conditions, which the organic product will form depending on those conditions, and the reaction conditions we're talking about are distillation and reflux. I'll give you a quick recap of these two techniques. Let's talk about distillation first, which is the process being shown now. Here we can see the primary alcohol being added to the oxidation mixture of acidified potassium dichromate. And what you can see here is, as the aldehyde is formed, it's being distilled out, and you can see the same process happening over here when the dichromate is remaining behind, preventing any further oxidation occurring to the carboxylic acid. In the case of reflux, we have a different situation. We have the aldehyde being formed by the continuous heating of the alcohol with the dichromate. This aldehyde is then refluxed upwards. It then refluxes down, reacts with further dichromate to form the carboxylic acid. As you can see in this process, there's no way the aldehyde can escape. It can only go back inside to further react to form the carboxylic acid. For the next part, we need to include the reagents observations in our answer, including the equations. The reagents are acidified potassium dichromate. The observations that are required are noted here, in which the original orange colour will go to green or blue in some cases, and that is only true for primary and secondary alcohols. Tertiary, recall, will not change color. For the equation, you need to note that the acidified dichromate is represented by oxygen in square brackets. Water will always be formed as a byproduct, and where does this water form from? One oxygen over here will take the hydrogen from here and one hydrogen from here to form H2O over here. Under reflux conditions, we have two equivalents of oxygen as opposed to one equivalent of oxygen, or you could say you have two equivalents of the acidified dichromate as opposed to one. You still have the one water molecule formed, but this time, because you had two oxidizing agent equivalents, you now form the carboxylic acid. Remember, this particular process is happening here under reflux conditions. For the bond angle in chloromethane, we first must understand the 3D structure of chloromethane, which is shown over here. Note carefully how I've deliberately made sure that the carbon-chlorine bond, which is this over here, is significantly longer compared to the carbon-hydrogen bonds. Any bond which is longer compared to the other bonds is going to be weaker. So if we were having nucleophilic substitution in this particular reaction, this is the bond, the long bond or the weak bond, which would have broken. Back to the original question about what the bond angle is. If you note, you will see you have no lone pairs over here. However, you do have 1, 2, 3, 4 bonding pairs. Any molecule in which you have 4 bonded pairs and 0 lone pairs, the bond angle will be 109.5 degrees. In part B, we are asked to deal with the mechanism for the reaction, which is nucleophilic substitution. Now, substitution means one particular atom or group of atoms will leave the original molecule and another one will replace it, very similar to how it happens in a football match. Now, in this particular case, let's start off by putting in the dipoles first. Carbon here will be delta positive, chlorine will be delta negative. We will then have the lone pair of the nitrogen from the ammonia react with this carbon over here, and again keep in mind this lone pair making a new bond here means that an existing bond must break from here, which will be this situation here. So you'll have a carbon-chlorine bond breaking with the electrons from the bond going towards the chlorine to form a Cl- ion over here. This whole molecule here is what has been added across over here. The term nucleophile, as described earlier, is simply an electron pair donor. Most students found balancing an equation for the overall reaction extremely difficult. However, in reality, it wasn't that hard, and I'll try to explain the easiness of this situation. Let's first of all ask ourselves, where did this particular reagent come from? That was actually given to us on the previous page over here. As for ammonia, well, again, that was given to us in the mechanism on the previous page. Where has this particular product come from? Again, this was given to us on the previous page as part of the mechanism. And finally, as for ammonium chloride, well, here's the ammonium ion again on the previous page, and there's the chloride. Collectively, ammonium chloride is formed over here. Name of the organic product. As there is only one carbon in the product, it will be a methyl, and there's one NH2 group, therefore amine. Equally, you could call it methane because it has one carbon atom with one amine group, giving it a name aminomethane. What would happen to the rate of reaction? Well, again, as I described earlier on in this paper, you can imagine the carbon iodine bond to be of a certain length, and the carbon chlorine bond would be of a shorter length. A longer bond is weaker than a shorter bond. If a bond is long, it is weak, and therefore it will break quicker and have a faster rate of reaction compared to a shorter bond. The reagents and conditions in question 5 are simply a case of recalling from memory. In the double bond over here for the alkene, you'll add across hydrogen with either a nickel, platinum, rhodium or palladium catalyst. I would actually advise to simply stick with nickel only, as that's the answer that is always going to be acceptable. And again, you'll have the hydrogen adding across the double bond over here, and this is actually going to put a hydrogen. One of them will go here and the other one will go here. Originally, if you look at it, it was CH3 compared to the CH2 and CH2 compared to the CH. For this reaction over here, you are adding across water, OH to one side over here. So this is where the OH is being added over here, and the H is being added over here. So one H over there and OH over there. In the last reaction, reaction 3, again my recommendation would be to stay with hydrogen bromide regardless of the other options which have been given in the mark scheme. And where does hydrogen bromide add? One hydrogen again attaching to the first carbon here, and a bromine attaching over here, as well as a bromine replacing the OH over here to form a bromine over here. And this particular part from there to there is nucleophilic substitution, whereas this part here is electrophilic addition. Question 5 is a typical electrophilic addition reaction with the bromine molecule adding across a double bond. So you have first of all repulsion of these electrons to these electrons, pushing electrons further away. That will cause this bond over here to break, and when this bond here is breaking, you'll have a Br minus formed, which is this Br minus over here. You'll also have a new bond forming between the carbon here and the bromine here, which is shown over here. In the last step, you will then have Br minus attacking the carbocation over here. Very important to make sure that the electron curly arrow here is starting from a negative charged bromine, or bromide I should say, and here again the actual curly arrow is originating from the bond going towards the delta positive bromine. Same here, the curly arrow must originate from the bond going towards delta negative bromine. This next question asks us to look into the oxidation of a dialcohol, as it's got one alcohol group here and one alcohol group over here, keeping in mind this particular one is a secondary alcohol over here, and this particular one is a primary alcohol, and a secondary alcohol can only be oxidized to a ketone. So if I just show you what happens to this one, the potential outcomes for this secondary alcohol could be a ketone, which is shown over here and over here. And then what you can have with this alcohol, which is a primary one, remember, is that the primary one here could be oxidized to either an aldehyde over here or a carboxylic acid over here. The skeletal formula for the ester butyl FNO8 is shown here. Just to put things into perspective, we have a butyl component which is 1, 2, 3, 4, and then we have the ethanoate component, which is 2 carbons, 1, 2, and of course that belongs to the ethanoate part. And remember, this particular part over here comes from the carboxylic acid, whereas this particular part comes from the alcohol. Calculation for the atom economy was a very basic process. You have the molecular weight of all the products, which is going here, and you have the molecular weight of the desired product, which is here, multiplied by 100 to give you the answer. The reagents for this reaction here, which is asking us to suggest how butanol forms butyl ethanoate, so it's an esterification reaction. Any reaction which forms an ester is always going to be an acid catalyst with the reaction heated or refluxed. The explanation for the percentage yield: any 2 points from these particular points would give an acceptable answer. Similar situation when it comes to 2 reasons for the butyl ethanoate is produced by process 1 rather than process 2. Any 2 points from the list here would have been an acceptable answer.